Okay, hello everyone. Welcome back to MLC. This is lecture 10 and the last lecture of this course. How time flies, and it's a great journey to work with everybody here in this virtual course or walking through the content of machine learning compilation. And to be honest, this is the first course of its kind, likely. And we also had a great deal of fun of exploring how we can teach it and how can we make the related course content accessible. So thank you for working with us throughout the journey. We will continue to improve the course content, iterate on the course future versions in the course, and you can continue to follow mlc.ai for the latest updates. In the meantime, you're also more than welcome to try and use some of the systems that we build throughout the course, namely Apache TVM, that can help us, hopefully can also help you to do future machine learning deployment use cases. Okay, so today we're going to do a summary and recap of what we learned so far. One of the things that that we learned about machine learning compilation is in this central theme, MLC is a process that for us to take machine learning models in its development form. In a lot of cases, the development form can happen in frameworks like TensorFlow, PyTorch, and JAX. And we are going to do a sequence transformations to bring those machine learning models onto a deployment form. In certain cases, the deployment form can be the same as development form. For example, if you are just going to build and run models in TensorFlow or PyTorch, those models will just run locally on the machines that you have. On the other cases, if you want to go and build and run the models on a different platform, for example, if you want to go and run on Android devices or other devices, there are different complications being involved, including things like fitting the new model deployment onto the API interfaces, building a set of libraries that allows us to have minimized dependencies so that we can execute on the target device, as well as being able to make use of the lower level runtime libraries like Android's OpenCL runtime or Android N library to really accelerate our executions. And a lot of machine learning frameworks, like machine learning deployment inference frameworks and machine learning training frameworks, also can take benefit of this MLC paradigm. As a matter of fact, if you think carefully, most of the machine learning inference deployment framework are doing some form of MLC inside the box. Okay, and in order to, it's really hard for us to cover all the possible instances of machine learning process on those frameworks. So on the other hand, the main theme of this course is trying to get us the basic elements and common terminologies. So it helps us to be able to talk about what are the possible MLC transformations and what are the possible abstractions out there. The second goal is we want to be able to make use of those elements so that we can compose different optimizations even for our own system. Right? So one of the key elements in machine learning compilation is, of course, tensors that serves as a runtime component that help us to be able to pass in the data across different layers, as well as tensor functions that encode the computation among input and output. Importantly, MLC is mostly about transforming different forms of tensor functions. Either in we have learned about computational graph form of tensor function that coordinates how does each of the element take your input and compute to output according to your data flow dependencies. In other cases, we have also seen tensor function that represent loop level computation, and we will be able to reorder the loops to get us better cache localities. We have also learned tensor functions that correspond to GPU threading model and making use of some of the GPU programming and help us to accelerate machine learning workloads on modern accelerators. All those things can be viewed as some variant of tensor functions. And one of the key things in MLC is we want to be able to build abstraction to represent those tensor functions and also transform among them so that we can get a tensor function that's very generic that represents maybe a ReLU operator, but without specifying how do we implement operators onto another variant tensor function that maybe fuse this in together and have a detailed implementation on how exactly we are going to do that on a low-level hardware. So the key elements in machine learning compilation, the tensor function, in the past 10 lectures, hopefully we have gone through many variants of them on how do we represent the end-to-end machine learning model. And most of the MLC process can be viewed as transformations among those tensor functions, right? Because usually in development forms, when we think about machine learning models, we think about them abstractly. In a lot of cases, we think about them as linear layers, softmax layers, and ReLU layers. Right? So we would not think about, hey, how I'm going to implement this linear layer using, say, AVX512 instructions on the hardware, or how I'm going to use CUDA kernel to implement the softmax function. So when we're developing things, we are thinking about things at a much higher level. However, when we start to go and really deploy them, we will need to start to worry about what is the target instruction that I'm going to use, right? Am I going to fuse the linear ReLU operator together as being shown in the slide, or am I going to just build them as separate kernels? Am I going to leverage GPU accelerations in this case? So all these questions are questions that we want to think about when we go and deploy a machine learning model. And of course, that is how I'm going to build another thing from scratch. Right? So MLC process is process that try to automate some of those things. And in order to do the automation, we want to kind of formalize it, in a terminology that machine also understands. Right? So from machine's point of view, MLC is just a transformations among tensor functions that can be represented using different abstractions. So in this particular case, we are transforming this computational graph of two-layer neural network onto another end-to-end neural network, right? That contains a fused linear ReLU layer, and also supplying additional linear ReLU implementation in this case. So most of the MLC process can be viewed as this kind of transformations, and then our question is mainly about how can we go and implement those transformations, and what are the different kinds of transformation we can leverage, right? So that we can for different purposes. In certain cases, it's about how do I go and have a better implementation of a lower level operator. Sometimes the lower level operator implementation will naturally imply possible constraints on the computation. For example, if a lower level operator expects fusion, then we want to be able to perform computational graph transformations to also transform the higher level part to leverage fusion in this case. So the overall MLC process effectively can be summarized as development, transform, and build, right? So most of the cases in the past lectures, we have gone through each of those phases. Specifically, we want to be able to summarize everything as a centralized data structure called IR module, which represents a collection of programs, collection of tensor functions we are going to do in transformations. And the good part about it is it makes a lot of things modularized, and it allows us to think about things in an incremental fashion. For example, we don't necessarily have to think about, hey, I'm going to directly take these models and figure out all the specific problems, like how I'm going to map the GPUs, how I'm going to allocate memories, how I'm going to go and handle operator fusion and so on. You can do them in several steps, and each of the steps is a transformation that we have to do. After we finish the transformations, then we will be able to take the IR module and build and run it. If it's a interpreted case, we just need to go and execute the specified updated execution form. Right? So most of the MLC process can be viewed as these transformations among IR modules. And one of the differences that we are doing in these lectures, we want to be able to, in this class, is we want to be able to also let you understand what's happening under the box, right? So usually the transformations among those IR modules are hidden behind the scene of the machine learning framework, the machine learning deployment, the machine learning inference engine, and so on. But really, you will find that a lot of those things can be understandable by developers, and sometimes it's helpful to understand those things. For example, if you want to guide quantization transformations, or in certain cases, if you want to choose among transformations, it's not necessarily very straightforward, or maybe the underlying system is not smart enough to figure out what kind of transformations you want to have. And in this case, it's really helpful to also allow developers to come in and also collaborate with the system. Another thing that this kind of modular transformation helps you is that usually those transformations also being built and specified by different engineering groups, audiences. For example, we could imagine that library builders and hardware vendors provide some part of the transformation that maps the lower level tensor IR functions and tensor primitives onto the hardware acceleration primitives, while the machine learning engineer provide a high level transformations, right? That does things like operator fusions and also specifying the corresponding computations that we're interested in. So having the ability to expose the set of transformations will give us some more flexibilities and make the overall MLC process more accessible. When we talk about MLC transformations, there are two things we want to think about. The first thing is the norm, right? So what is the input output of each of the transformation? Throughout this lecture, we have focused on the nouns, what we call IR module. Effectively, IR module contains a collection of functions, or tensor function in this case, that can represent machine learning tensor functions in different forms. For example, throughout the course, we have learned how we can use tensor IR functions to represent multi-dimensional loops, as well as tensor programs. This kind of multi-dimensional loops is really helpful for us to specify low-level details of implementation. So we'll be able to run automatic tunings on them, or trying out different variants of loop ordering, vectorization, and prioritization. And usually, this type of loops is very powerful for us to do effective code generations in this case. Another important factor is library functions, like calls onto the environment linear or callback onto the torch function. This is because in most of the machine learning frameworks, libraries are still being very powerful, and we really want to also collaborate with machine learning system engineers and HPC engineers who have the common wisdom to be able to come up with those libraries. And so being able to represent the calls onto those library functions is really important for us to be able to generate transformations that contains those library functions. Finally, one of the important things is we still want to be able to build the computational graph that represents a high-level computation that trains everything together, and also contains high-level primitive operators like relax.n.value that represents just a computational graph node of value operator. These high-level operators are usually helpful for data scientists and domain engineers to be able to quickly specify the high-level inputs onto the system. In the meantime, there are usually cases where we want to be able to say customize a certain operator that are not available in high-level operators. That's where things like tensor functions library, directly invocation of library comes in handy, because we will be able to represent all those things in a single computational graph. And one important thing that we keep coming back in this class is also about interaction. So how can computational graph interact with the tensor functions, and how can it interact with library calls, right? So in this case, at least the ability to be able to represent a computational graph and a high-level operator and library function is very helpful. Once we have this, we'll be able to do transformations like take high-level value operations and map it onto a library function calls, right? That calls into library, and that could be a very interesting project. If you are interested in doing a follow-up project on the course, like take a high-level model that contains all the possible high-level operators and try to map them onto libraries like CODN or in the case of mobile devices like NCN and other library functions, while still leveraging the MLC infrastructure to do a lot of optimizations. Or even more interestingly, right, try to map the calls on library function together with the calls onto Tensor functions that allows you to do a bit of code generation together with the library function calls. So these are all the interesting possibilities that MLC enables. And the first step to enable that is have a common noun that allows to represent all the possibilities throughout MLC processing. That is IR module and the related abstractions we have on this. Once we have a noun, the next thing, of course, is a verb, right? We want to be able to transform across IR modules, because an IR module contains all the ability to represent both, Tensor functions, the library functions, as well as computation graph high-level operators, and also calls among them. We can take an IR module and run it through different transformations. A lot of the machine learning compilation process now becomes just a transformation from an IR module to another IR module. I will give a few examples that we have learned in the course. For example, in the first few lectures, we learned about Tensor IR level transformations, right? Using what we call Tensor IR schedule and meta schedule that gives us all ability to do auto tuning and takes existing functions, try out different possibilities, and then go and find the best one among them. We can also do computational graph optimizations that takes a computational graph and then generate another computational graph that, for example, fuses two operators together, or in other cases, trying to allocate memories among them, or being able to, plan the execution orders of certain operators if they are parallelism involved. And during compilation, of course, in different stages, we can choose to map part of the computations onto library functions we're interested in. We want to quickly try things out, and also mix it with code generation approaches, so that we'll be able to try out both library functions and code generation and have them work together. So transformation is really at the center of all the MLC process, and the ability to be able to represent all those code and being able to build those transformations in an incremental fashion is really important for us to build a robust and continuously evolving machine learning compiler. If you look at the set of transformation that existing approaches do, for example, in most of the machine learning frameworks, the common approach that machine learning frameworks do is they will just go and first import the computations onto a high-level computational graph stored in an IR module. Well, usually different frameworks have their own terminology, but stored in an IR module that represent the computation. And then machine learning frameworks will go and do some computational graph rewriting, like replace fusions, determine the layout of the computation, and so on. And finally, most of the machine learning frameworks will go and map some of the operator calls onto library function calls. So they will directly go and invoke the heavily optimized libraries that people build, and effectively, when we are building the end-to-end executions, it will run into like end-to-end interpretation of the library function. Throughout this class, you can find that we are doing everything in Jupyter Notebook, right? Except the first and the last lecture. Most of the things we are doing are handled in Jupyter Notebook. So it's a bit not very typical in a sense that most when you think about compiler, think about something like you invoke from command lines, and you want to build everything as a black box that people go and directly invoke on. What we believe is that we want to be able to also enable some interactive transformation, because a lot of cases the machine learning engineers and users also have a great amount of knowledge on how this optimization can be used. And there are also different kind of transformation we can do. For example, maybe you want to just try things out in a loop so that you can try different optimizations, compare among them, and pick the best one. Because MLC process is still a very emerging domain, so there's not really a silver bullet answer of, hey, these are the set of transformations, and these are the set of things you do. And once you do that, you will get the best performance and the best solution. So we really want to enable different kind of possibilities in here. And the way we enable that is trying to be able to have an IR module that can represent different possibilities, be able to represent them in TVM script, a Python ASD dialect that you can directly go and interact with in Jupyter notebooks, and build separate transformations in Python or in C++ so that it get exposed to Python, so that you can go and play with all those interactions and see the effect before and after. This is a new way of trying out machine learning compilations, and it's also the first time we ever teach in the course. So we will see what other things that it can enable. But hopefully throughout the course you can get a feel of this kind of interactivities, and it will become a kind of normal Python workflow that you can go and interface with your normal machine learning build and the deployment flow. So let us know if you have more ideas on how this kind of interactive transformation can be used. And what we believe is that being able to enable this makes it more accessible and helps more people to getting started to use MLC in a Python first fashion. Okay. So finally, I want to talk a bit about future directions. Of course, MLC is an emerging theme, and it's not possible for us to talk about all the possible techniques that are being involved. The goal of this course is really to give us a glimpse and talk about the basic principles. Basic principles include the tensor program function abstractions. How can we have different abstractions interact with each other? And then being able to formalize most of the MLC process as a transformation among those IR modules interactively in Python notebook. And there are, of course, a lot of exciting future directions that are still being worked on a lot of machine learning compilation researchers as well as machine learning system researchers. For example, one of the things that folks are looking at is how can we have talked about several layers, right? How designers go and build how specialized layer that we talk about in one lecture. The machine learning engineers might be interested in building the engineering, the computational graph optimization part. And then, in certain cases, maybe you want to try out auto tuning, so we are going to leverage Tensor IR and so on. Previously, traditionally, most of the framework try to structure the computations as we will call multi-stage lowering. So you start with a computational graph, you go and do certain transformations there, and you map everything onto the Tensor IR functions. You do something further, and then you map them onto lower level libraries and so on. Really, we want to be able to enable feedbacks and optimization across those layers. So not only we try to have this clear boundary, we want to be able to break the boundaries. We want to be able to have IR module that contains both Tensor IR function computational graph, so that, say, if I want to do optimizations on certain Tensor IR functions like layout decisions, you will be able to flow it back onto the computational graph. And this is very important for specialized hardware. Of course, one of the important themes, how can we build a smarter and more automated approach to support specialized hardware like DSPs, machine learning accelerators, or even GPUs that come with like tensor core-like abstractions. Tensorization is one first step, and there are a lot more work we can do to automate this process. And more importantly, a lot of cases, we want to start to think about how can the engineers and users collaborate with the compilation system. This is because machine learning optimization is becoming so interesting that we can really benefit from knowledges from HPC engineers and others that write libraries, have ideas of how we want to do approximate optimizations like quantization and other things, while a compilation solution can offer certain level of automation to support them. For example, be able to handle out end-to-end layout deployment solutions with a few hints, leverage microkernels to build by HPC engineers, but still make use of automated solution to figure out tilings and GPU thread mappings and so on. So the collaboration between engineer and compilation system will be a common theme that we will see more and more in the future. That's why I believe that interaction is so important. That help us to build the entire MLC flow in Jupyter Notebook. Many ideas can be, and one important part that I think come back and why it makes so exciting, just like machine learning frameworks that offers you the ability to build up things like residual module detectors and build a separate and then connection together in an organic way. Many of ideas in MLC process can be achieved through incremental transformations among IR modules, and by having a common set of abstraction that connects everything together, it allows us to be able to, collaborate more easily. So that in certain cases, I will be able to build a fusor that only fuses two operators together, and then bring that together with a very generic version of fusor that fuse the rest of the things. Or I can work with part of optimization that feed onto the hardware engineer to work on the rest of the part. So the ability to achieve most of the things in this transformation paradigm and being able to export into Jupyter Notebook so that you can observe what's going on will allow us to really make it MLC process more accessible. So hopefully this will become part of a daily machine learning workflow in the future. Moving forward, we will continue to improve this course. So do follow us on mlc.ai, and you are more than welcome to also check out the related course materials, give us feedback, and use the course content to build something that might be useful to you. Let us know. We'll definitely love to know, what the things you build, and take a look at Apache TVM, which will continually bring in some of the learnings of the course onto the project as well. In the meantime, if you're also interested in building machine learning systems in general, there are also other courses you can check out. In the incoming fall, I'm going to offer a course at CMU called Deep Learning Systems that teaches you how to build end-to-end PyTorch-like deep learning system from scratch, and that's also going to be quite fun. A lot of principles we learn in this course will also help us to go into that course as well. Okay, thanks everybody for awesome joining in the summer. I really enjoyed building all the course materials and really start defining the machine learning compilation together. And I'm looking forward to continuing work with everybody as a part of MLC, and hopefully we'll also see each other in both physically, virtually, and see more use cases of machine learning compilation in the machine learning ecosystem. Thank you.